Looks like we're all set, and it's 4:20 by my watch now, so I expected this would be a small crowd, a self-selecting crowd. This is a very niche topic, but hopefully you'll get something interesting out of this, this whole discussion. We'll be talking about, well, you can read the slide, anchored metadata. So this is maybe a topic you've never come across before. I certainly never had until we started looking into it a year or so ago. My name is Austin Bingham. I work for and half own this company, 60 North. We do a lot of Python work, consulting, training, things like that, and this came out of some of our sort of internal development, some ideas we've been tossing around for a while. I'm at a disadvantage here because I like to point at screens when I present, and I can't really do that in this. So I'm going to try to use this little pointer. So if you see me getting flustered, that's part of what's going on here. So what is the problem I'm trying to solve? I want to associate metadata with my code, and this is something we do on a pretty regular basis. So I've got some code here. Can anybody tell me what language that is? It's one of the hot new things, right? That's Rust, right? I didn't know much Rust until I started working on this. We might want to be able to tag parts of our code and associate data, saying, you know, please don't mutate this if you're doing mutation testing. So I don't want that bit of code, just those 5 characters there, not the whole line, but just that little bit to not be touched. Or maybe I don't want linting to apply to that bit of code there, or maybe I want to disable testing on that bit of code for some reason. There's lots of reasons we might want to do this kind of thing, and it comes up over and over again. We found this problem specifically when we were working on a tool called Cosmic Ray. Cosmic Ray is a mutation testing tool for Python that we've been working on for actually quite a long time. So to motivate this a little bit, I want to talk about mutation testing very briefly, because it's interesting in its own right. So what is mutation testing? If you've never heard of it, well, you have some body of code under test, your application, your library, something like that, and you have a test suite that tests it, tells you that it works correctly. The idea of mutation testing is that you make a single small change to your code, perhaps change a greater than to a less than, or a 1 to a 0, or something like that, and then you run your test suite. And if your test suite is good, if it is able to tell you that your code is actually not functioning properly, what you get is a test failure at that point. So if you have a test suite, a very high fidelity test suite that can actually detect all changes in functionality in your program, any small change like that should result in a test failure. So this is an interesting problem in its own right. It involves all sorts of complex problems and has been a real joy to work on. But we have a particular problem, and this is not just for Python, but this is the theory of mutation testing, this notion of equivalent mutants. One kind of equivalent mutant that shows up in Python regularly is what you see here. You don't have to really know Python to appreciate this talk, but this is code that is it's the main block of a Python program. And it's only executed if the module that you're executing is the main module, which might be the case when you're running the program, but is never the case when you're running your test suite. So any code in here that the mutation testing tool modifies will never result in any change in your test suite output. So we have to somehow tell the testing tool or the mutation testing tool, please don't futz with this code right here. That's a common one. This is another one that's a little bit more devious. So stare at that and anybody see what the problem is? Of course you don't see what the problem is. It's very, very subtle. Maybe you do see it and you're very, very smart. The problem in this code from mutation testing point of view is that 0. Cosmic Ray is going to plow through your code looking for numbers and things that it can mess with. It's going to see a 0 and it's going to change it to a 1 or 1,000 or -6 or something like that. What's going to happen is an almost completely unobservable change in the behavior of your program. What this function is doing is consuming an iterable just to get the side effects. It's doing nothing else with the iterable. And this is just a technique. This is just an idiom for constructing a double-ended queue and ramming a bunch of stuff through it to get it to be processed. Right. If I change that 0 to a 1, it says that the double-ended queue can now go from size 0 to size 1. That's great. The only way I could ever detect that is to analyze essentially Python's internal data management structures that you never really want to look at unless you're a CPython hacker. So this is another undetectable change. It's a legitimate change that the mutation testing suite could make, but it's impossible to test. So how do we tell Cosmic Ray not to touch that? How do I communicate that to a tool? This is the core of the problem we were trying to solve. And And this has been going on for a long time. If you look at the timestamp on this GitHub issue, it goes back to 2015. It's like there are cases where I know that there are completely acceptable failures that I need to avoid, let the user tell me about, and not run tests or not run mutations over certain parts of code. I thought hard about this. I thought for a little while at least, and I realized that I could have a separate file that says at line such and such in file such and such, don't mutate or don't apply specific mutation operators to this range of code. I said this would be very brittle because the code will change over time. How do I maintain those things? So I thought about it and kind of abandoned the idea and moved on. The alternative, one you've probably seen, is something like this. I put these no QA, the hashtag here, I'll try to use the pointer for the first time. These kinds of things. Comments. Telling the linting tool, for example, please don't run linting on this bit of code. So you've probably seen this in Python or whatever other language you work in. It's very common, and it works. It works just fine, but it has some problems, what I call inline metadata here. Here are the problems. One is that it's language specific. If I write a tool to do that, it has to be written for a specific language because it's using the mechanisms, the syntax of the language to communicate the metadata. So if I write it once for Python, I have to do the same thing for Rust or the same thing for Perl, God forbid. I'm not supposed to bash other languages here, so I won't do that anymore. But there can also be collisions. What if I want to say two things about this line of code? I want to say no QA and don't mutate. How do I do that? Maybe they can live side by side. Maybe they will somehow shake hands, but I don't know that that's really built into how these metadata facilities work. It clutters your code. This is something I just don't like on an aesthetic level. It's ugly. I think it kind of takes away from the joy of writing Python when I have to put other cruft in my code. And to a degree, it's not robust against refactoring. If I make refactorings, those little tags, those comments will follow the lines of code along, maybe, but if I'm using a refactoring tool, they may not follow this along. So actually, they seem robust, but they can break if you start using tools that help you do proper software engineering. So there's a number of problems with this approach, and we wanted to try to explore the other option. That's why it was appealing to externalize this metadata, this approach we're talking about here. So the solution, there's a question mark there because this seems to work. What I'm going to demonstrate and show here in this talk does seem to work, but it hasn't really been used very broadly. So I was having a discussion at Accu in Bristol a couple of years ago with these two guys, Rob Smallshear, who's sitting right over there, and David McKeever, who, if you've never met David, you should meet him. He's a great guy, very, very smart. And we got talking about this problem and started tossing around very seriously this idea of externalizing the metadata. And of course, to have a proper discussion, we had to be official about things, so we had to have some beer as well. And this really got our juices flowing and got us thinking about how we might do this. And it seemed like more and more of a tractable idea. If you could just find a way that as your code changes over time, which it inevitably will, you can automatically move your anchors around, your metadata. I can give you some foreshadowing. We'll talk about something called anchors here in a little bit. So the idea, very straightforward. You got your source code, and you've got some external file containing the metadata, and it says, at this place in the source code, don't do mutations. At this place in the source code, disable a certain kind of operator. And this by itself is very simple, but it still doesn't address the key question, what happens when the code changes? I like this slide because this is obviously Achilles. So two things you can observe. Achilles worked out. And also arrows were huge apparently back then. Look at the size of that thing. I mean, you get hit in the heel, you get hit in the pinky, you might die from something like that. I don't know if that's actually to scale, but it looks like a big arrow to me. Anyhow, this is the Achilles heel of the externalizing problem. How can you have the computer do automatic updates rather than forcing you to keep your anchors up to date with your code? That's what we wanted to avoid. So, the challenge. How can I keep metadata aligned with changing source code? Source code will change, and the metadata needs to follow along or be ablated when it no longer matches, that is, dropped off when it no longer matches the code. I was able to put this problem off for a long time because the backlog of issues for Cosmic Ray is pretty substantial, and it's a part-time hobby project, so we don't put a lot of energy into it most of the time. So I was able to kind of convince myself I shouldn't work on this. But after I'm not exactly sure why I got inspired, but I did get inspired to do some reading about this one afternoon, and I found this wonderful paper from the Czech Republic by Karol and Maria Bielikova. I don't know if I'm pronouncing that right. She seems to be the head researcher here because she has many more citations and publications. And this is exactly what I was looking for: metadata anchoring for source code, robust location descriptor definition, building and interpreting. Great. So it was a very, very promising paper, and I read the paper, and it kind of struck me as something, hey, I could do this. I understood the algorithms. I understood the concepts they were talking about. It wasn't too far out of my comfort zone. It felt like something I could program. So I said, okay, I'll give this a shot. What's the basis of the idea? The basis of the idea is you have this notion of a context. And the context includes three things. I'll try the pointer again. You have what we call the topic. I kind of made this term up for myself, but it comes from other ideas in their paper. The topic is the thing that you are anchoring. This is the range of code I don't want to mutate, or that I don't want to lint, or whatever. And you just remember what that text looks like. You store that. And you also store some text from before that and some text from after that. So, 10 characters or 20 characters before and after the topic, so you can understand the context, what it looked like when you made the anchor. And this is what gets stored off to the side. This is how you point to a piece of code. The real magic, though, the real trick that they brought to bear on this is this thing called the Smith-Waterman alignment algorithm. Smith-Waterman is an algorithm from genetics research, and its job in genetics is to take two sequences of nucleotides and find out how they match up, how they align. So you can try to start comparing genes. I don't know exactly what they use it for, but it is a well-established algorithm. It has lots of good implementations, and it's quite fast, and it gives really good results for what they do, and it seems to give good results for aligning pieces of source code that are similar but not identical, which is exactly the problem that we had. How can I take an original piece of source code, a changed source code, and figure out where they touch? Are they still mostly the same? This was the problem we wanted to solve, and they seem to have found a good algorithm for it. So there's a couple of data structures and algorithms, so we're going to go back to CS 101 here for a little while. The first data structure we have in this work, the tool is called Spore, and we'll get to that in a little bit, is, okay, the topic. We remember the string. We remember the text that we're anchoring. We remember the offset into the source file where that starts, and we remember some before and after text. Again, 10 to 20 characters, something like that, so that we can remember what the file looked like. There's some nominal width to this beginning, and I almost reached down to point at the screen. That wouldn't help you very much. There's some nominal width to before and after here. So it could be that the topic is right at the front of my file, and I can't have all of the before that I want, but I remember how big I expect it to be, so that if the anchor moves, I can actually get the correct amount. So we have to store all that information for each anchor. The data structure looks, it does look kind of like this, but if we were going to anchor this code, again, some Rust code, I might have the topic pointing to that line, so that's, 15 characters, something like that. I would remember some 10 characters before that, 10 characters after that, and an offset into the file. So that's how I point to a location in a source code file. Associated with that is a bigger data structure called the anchor. So the anchor has a context inside it, and that's how it knows how to point to something in a file here. It remembers where the path is, the encoding of the file. This is actually really important, because if I'm talking about offsets into a file, I'm talking about bytes typically speaking, I need to know the encoding, so we have to store that. And it also stores the actual metadata. So this is the thing, this anchor is the thing that says, I've got your metadata, and this is the code that it applies to. So none of this is terribly complicated. Yeah, this is just simple data structures, but these are, it took a little while to get to exactly this shape, and it's worth understanding these bits. So with anchors in place, if I can create an anchor to point into somewhere in a source file, how do I take a changed source file and get the anchor to point to the right place? That is where the algorithms come into play. Well, the important algorithm, Smith-Waterman. I think it's really interesting. It's kind of a fun thing to talk about these details in a sense, because I don't think we get a lot of this at these conferences. This is pretty low level. This is very computer sciencey. It takes some people out of their comfort zone, hopefully. It certainly was entertaining to write. So it is used in genomics, as I said, for aligning sequences of nucleotides, GATTCA, those things. It finds all optimal alignments between two sequences of nucleotides and reports them back to you. And then it applies some gap penalties and scoring functions and stuff. There's a few knobs you can twist on the algorithm to kind of coax it to do the right thing for you. And there's some research to be done in that for anchored metadata, of course. And it uses some backtracking to help you find the optimal alignment between two things. Not just optimal scores of alignment, but the actual alignments between the two, either sequences of nucleotides or source code files. So the basic idea, and this is at a high level, we'll see some diagrammatic explanations in a second that really make this much clearer, I think, is for each pair of input elements, we have a matrix, n by m matrix, and for each combination of the Cartesian cross product, whatever you want to call it, we calculate a score. And that score is based on how well those two things match. So is it an A and an A? That matches really well. Is it an A and a G? Those don't match at all. And the score is based on the path we followed through the text so far to get to that point. So if we've been following a long, contiguous streak, our score is going to be really high. But if there have been discontinuities, the score will go down as a result. And this is how it can deal with bits of code that are similar, then dissimilar for a little bit, and then similar again. So if you inserted something into your source code, it can detect that, and it can remember to update your anchor. If there is, as I just said, if there's a contiguous streak of matches, then you get very high scores, and there's a gap penalty if there are discontinuities. That didn't work. You can get maximal scores. You can get more than one maximal score. That is, they have the same score, and they're the biggest of all the scores. And so you might get more than one match back from the algorithm. This is important. This is an area I haven't explored much, but I need to think hard about it. And we can use backtracking to figure out the actual path. So it's easier to understand with a demonstration. So let's take two sequences of nucleotides, GACCG and GCCA. Just intuitively, we can kind of see where these are going to match, right? You can see, okay, we see GCC and we see G and CC here, and we kind of figure that's kind of how they're going to line up. And in fact, that's exactly what happens in this case. So we can eyeball it. We've got brains and eyes, but how does the computer do it? Well, it does it kind of like this. So we build this matrix, and I hope you can see that. We've got the first series here, GACCG along the top, and GCCA along the side, and this is the scoring matrix. We're going to fill this up with scores as we go along. So we initialize this outer band with zeros. So this outer band is fine because it's zeros because there's no actual nucleotides represented there. It's just the baseline score that we're going to try to increase as we find our path through things. So the first place we want to find a score is for G and G. All right, so obviously those match, and so following this little algorithm here, the score at this cell is the maximum of either the score at the diagonal here is 0, so looking up at this diagonal here, plus the score function, aibj, or the gap penalty plus the scores at the sides. So we're trying to find the best way to get from one of our afferent neighbors, we would call these, into the cell we're trying to score. And score functions, these are just example score functions. They don't have to be these, but 3 if a is equal to b, otherwise -3 for the score function, and a gap penalty of -2. These are our other knobs we can play with in the algorithm. So if we run that algorithm for this first cell here, G and G, we get a score of 3. We get not just a score of 3, but we get a back pointer to where we came into this from, where we got that maximum score from. So the algorithm said, these are the same, and so you got the score of 3 plus your incoming 0 here that gives you a 3, and I remember that error for you. It's possible to have 2 arrows, maybe even 3, coming out of any of these scored cells. So we have to keep track of those, and these are the arrows we follow to do the backtracking later on, to calculate the actual match. We then move through the grid left to right like reading a book, and we fill it up with arrows as we go along, and ultimately we end up with something that looks like this. And our job now is to scan through these numbers and find the biggest score or the biggest scores. So here we get 7. That's the biggest number in this graph, and so it's the winning score. But there could be multiple 7s or multiple 13s, whatever the high score happens to be. So now that I found 7, my job is I found a good match. That's a pretty good number for this kind of small size input. I need to go back through the arrows and follow it until I hit a 0. And if I do that, I end up with something like this. And this backtrack tells me how GACCG maps to GCCA. If I look at that now, I see that G matches to G, great. This A matches to C, but we would call that a discontinuity because it's not going on the diagonal. It's going on, here it's going horizontally, or it could be going vertically. And then we continue on the diagonal, and we build up our backtrack. And so now we have this C maps to this C maps to this C. So that's the GCC mapping to GACC that we intuited earlier, or that maybe I tried to convince you to intuit earlier, but that's what I saw. So this in small, this is how the algorithm works, and it's just bigger for source code or for big nucleotides. And so we end up with this alignment, which is what we intuitively expect. And it's that intuitiveness which is interesting here, because that's how we would match. If I was to take an anchor and try to match it to a new bit of source code, I would have to be working in an intuitive way there as well. It has to match with how I think. Otherwise, it's just computer noise. It's machine learning gone crazy, which it kind of has, I think. So that's kind of neat. I think that's an interesting algorithm, and it's interesting that we have applications for something like that in computer science and in programming, and so I set out to write that. So how do we apply that to updating our anchors? It's a pretty straightforward process. We take the context. Remember, a context is the before bit, the topic, and the after bit, and we align it with the new source code. Where does this context match best in the changed source code? And that gives us some location. I then take, within that match, where does the topic from the context align with the new source code? I then use that to calculate the offset and create a brand new anchor, a brand new context, and align that topic with the new source code, and I have a new anchor, and we are set. This is implemented, as I mentioned earlier, in a tool called Spore. It's implemented twice, really 1.5 times at this point. Something we've written, and you are welcome to go check it out on GitHub if you want. So there's a Rust version here, Rust Spore, which I probably just should call Spore from now on. It is the official version. It's the one that I'm updating and maintaining and working on. The initial work was done on a Python version, which still kind of works. So I think the data structures have drifted apart a bit. And the big problem with the Python version, of course, is that it's slow. I love Python. I use it all the time. It's a very powerful language, but running fast is not its forte. Running fast is something that Spore is really good at. And so I realized that the utility of a tool like this was going to be based on how fast it could run. Because I'm in an IDE, I'm typing along, I make a change, and I save, and I want my anchors to maybe automatically update. That needs to be as fast as possible. So rewriting it in Spore was sort of an obvious answer. Well, if I mean practical, rewriting it in C++ is the obvious answer, because I know C++. I don't really know Rust. But this was a good chance to learn Rust, so it was a good experience. And it's a beautiful language in many ways. We'll get to that in a second. How does Spore work? Again, not a lot of rocket science behind it. It creates, for your project, a .spore directory, much like a .git directory or something like that, just a place for it to put its data. Inside that directory, you have a bunch of YAML files that have UUID file names. I needed unique file names, because you could imagine renaming the files in some sense, encoding the location inside the file in the file name here. But we might have multiple anchors that point to the same thing but have different kinds of metadata coming from different tools entirely. So we just use UUIDs, because we can generate those for free and forever. And inside each of these files, you have some YAML, and you can see all the bits and pieces here of the data structures we talked about. So the topic is right here, struct con, some after, and some offset, and so forth. And here's the metadata. It's just a dictionary, mutate false. So Spore doesn't care what that metadata is. All it promises is that it will maintain it for you and give it to you when you ask for it. It's up for a tool like Cosmic Ray to have some integration with Spore to go, okay, I'm about to mutate this place. Am I allowed to do that? Give me the metadata for this range that I'm about to look at. Is there anything I need to know in there? So Spore is very hands-off in that sense. It says, I don't know, here's some data, you make your decision based on that. And there could be other tools besides Cosmic Ray using Spore and the same Spore directory for their own purposes as well. So again, no rocket science, nothing complicated there. It has a command line interface that is very similar to tools like Git. I think Git has a very good model there. So you can do things like initialize your repository. You can add anchors to it, list them, do details. And critically, you can do update. That's the real magic bit there. We say, please look for any anchors that are out of date, that don't match their current source files, and try to align them again, and tell me if there's any problems with that. OK, so this slide says demo. I would like to do a demo, but this is a shorter format than I originally wrote this talk for. So what I'm going to do is go through the rest of the talk, which is not hugely long, and then come back to the demo in a second. I like that picture quite a bit. There's quite a bit of work that I would love to do in Spore. And if anybody is feeling energetic and has time on their hands and wants to help, I would love to have your help. Excuse me. Some of the obvious things that Spore should do is integrate with an IDE. So this is a mock-up of integration with Visual Studio Code, and it'd be nice if you could turn on Spore mode and it could highlight bits of code and say, yeah, you've got a tag, an anchor there, and you can edit that anchor if you click on this button. And then it could just do the work of calling out the Spore and doing things it needs to do. I don't think this would be terribly difficult. I mean, I've looked a bit at doing this kind of integration with Visual Studio Code, and it's not all that bad. They've done a really good job, actually, of making it very approachable. There are other sort of conceptual things we need to think about. One is anchoring directories. Right now, we don't really have that ability, but it might be nice to be able to say, just completely, I'm going to put some metadata on this directory and just don't do any mutation there at all, for example. I don't think this is going to be terribly difficult to accomplish, but it's something I haven't given a huge amount of thought to either. Ultimately, I think it's just another kind of anchor that has some Boolean that says this is a directory rather than a file. It might be that simple. A stickier problem is the question of what do I do with renames, right? So in some sense, this just comes down to source control integration, but it's maybe a higher level than that even. So here I'm saying, git move foo to bar. Spore doesn't know that that's happened. All it knows is that it has a bunch of anchors that used to point to foo, and foo appears to have disappeared now. And so all it can tell you is that all these anchors are out of date. It might be nice to be able to integrate with tools like Git to say when you do a rename, when a rename is detected, can we have a hook that goes to Spore and says, hey, Spore, foo has become this, update all of your anchors. That shouldn't be, that doesn't sound too hard to do, but I know very little about integrating with Git, so maybe this is really complicated. But okay, well then I'll expect a pull request in the next week. Thanks. Yeah, I'm not kidding. No, I know where you work. I know your boss. He's not going to care, but no, it's ignoring the question of integrating with Git. The question of what to do with renames is a complicated one because maybe you're not using Git, maybe you're just playing around with some files. And so, how do we detect this? Are there heuristics we can run to determine that a rename has happened, for example? Maybe so. And there's a lot of other stuff that could be done. Currently, Spore is using a homegrown, me-grown Smith-Waterman implementation, which is probably suboptimal. This is one of the most highly researched algorithms in genetics, and it's really fast. Good implementations of it are super fast, so I should probably boot mine out the door and use a third-party one. Alternative tokenization. So if you go and read that paper that I initially got the ideas from, stole the ideas from, they tokenize their source code on words, on spaces. They tokenize whole words, and that's how they do their matching. My current implementation tokenizes on characters, and initially that was because I hadn't thought about the problem very hard, but then I started thinking that, well, actually tokenizing on characters seems to make a lot of sense, because what if I have an identifier, foo capital B bar, and I rename that to foo underscore bar, right? Now I can catch those realignments if I tokenize on characters, but not if I tokenize on words. But I need to understand better why they tokenize on words, so maybe there's some research to be done there, or maybe that should be just a knob we can twist on Spore, saying do alternate kinds of tokenization. I need to explore different kinds of scoring functions, and related to that, I need to think about function ensembles. So an example of this would be if I got two equally high scores. Say I got 7 and 7 for two paths through the match. How do I choose between those two? Do I ask the user? Do I just pick the first one? Or do I perhaps pick the one that seems to be closest to the original location? Or do I have a family of scoring functions that all contribute to a final score? This would be the notion of function ensembles. It's a really interesting topic, and I think that it's going to come, it's something we need to think about really hard if we start working with bigger bodies of code. Storing the anchor history, it might be useful in some cases to have essentially a log of all the locations an anchor looked at. Match quality warnings. So you've got a match, but maybe it's poor, maybe it's not very good, and we want to be able to warn the user that we've done an update, we've moved your anchor, but we don't entirely trust it. Maybe you should look at it again. This one is really interesting. If we could make this work, you can make it work in Lisp, I think, but maybe not in Python. Semantic anchors. Can I anchor a function? Can I anchor a class? That seems doable. I could do it in my head, but how do I teach a computer to do that? You can think about ASTs, you can think about all sorts of interesting approaches, but I don't know which ones would work best. So this is really an area that, if you could get it to work, would be super powerful. Then you're not relying on text matching, you're relying on matching patterns in the program, and I think that could be much more effective, much more realistic, give you better results, but I don't exactly know how to approach it yet. Again, because I haven't had huge amounts of time to think about it. So those are the kinds of open questions in SPOR in this entire area, as far as I know. So if you have any insights into that, you want to bang your head against a hard problem, join in. It's fun stuff, I think. So there's a lot of interest in Rust lately, and I think for good reason. And so I thought I'd spend a little bit of time talking about why I switched from Python to Rust. I told you the obvious reason, and that reason was speed. Right? Python is a great language, and I can think very quickly in Python and get the ideas down. And so I was able to use Python to figure this problem out, to find the edges and the angles of it. But then I realized it just wasn't going to scale properly. So this was the big reason that I switched to Rust. Also curiosity. Rust seems to have a lot of good ideas in it. If you haven't looked at it, it's worth investigating a bit to kind of see how they've pulled ideas from, some from Python, some from kind of the Haskell world, some from C++ and systems programming and D and places like that. And they pulled them together into, I think, a really nice synthesis. You get a lot of good qualities in Rust. You can avoid null pointers, things like that. At systems level, that's really, really useful to not have programs that crash. So it's nice in any program, really. So I was curious to see what it was like to build a substantial program in Rust. That was another motivation for it. As with any language, there's a bit of a learning curve, and you're going to do things the wrong way at first, and you're going to spend a lot of time on Stack Overflow trying to figure out how to make X talk to Y and work with their type system and their lifetime checker. They have all these new concepts you have to work with in Rust. Ultimately, though, if you have experience with C++, C#, Java, most mainstream languages, you're not going to be too far afield when you get into Rust. You're going to have to train a few things into your brain, but otherwise it's a very enjoyable experience, or I thought so as well. Overall, I found it to be very positive. I enjoyed working in Rust, still do. I still feel like I have a lot to learn. I want to do some more projects, but it's got very nice tooling, especially for a language that is so new. I basically fired up VS Code, which is what I use for most things nowadays, and a lot of stuff just kind of worked. There's no debugger. That's a problem. But the rest of the stuff, the packaging system and the ability to build and run tests and stuff was all very nice. It has a nice, quick development cycle, especially compared to large C++ programs. Very fast execution. It feels quite maintainable. And I think this is one of the goals they had when designing the language, was to make it possible to make big changes very rapidly. And they don't have great refactoring tools quite yet, but their compiler is good at catching, of course, compilation bugs, and the way the language is designed, I think, lets you model things the way your brain thinks about them, in a sense. I don't find that I'm not fighting class hierarchies and stuff as much as I would in normal class-oriented programming languages. It feels very robust. I definitely trust Rust code more than I would trust, say, C++ code. I mean, you can write C++ in a way that pointers are effectively hidden, but there's always that possibility that you've missed something. In Rust, you can actually never you can make it so you never have to worry about null reference or null pointer dereferences. You can, of course, shoot your foot off in Rust as well if you choose to, but they make it very explicit when you enter that zone. So it's a trade-off. It's well worth learning. I think that I learned a lot from the experience of switching over to Rust for something, and I think it was the right decision for this project. It's not the right decision for every project, of course. So, quick fly through of all that. I'm going to go back to, well, I don't really have to go back to this slide, but I will because I like the picture. Right, demo. Hopefully the demo does not turn out to be a train wreck, right? I put a train wreck up because what's the likelihood of 2 train wrecks being in the same room at the same time? Very small. So we've already got one. The demo will not be. That's the joke about the guy who takes a bomb on a plane with him, right? He said, why do you bring a bomb on the plane? He says, you know what the odds are of there being 2 bombs on a plane? Basically 0. So, genius. All right, I need to switch my, sorry, I've got new glasses and I'm still learning to work with them. Switch my settings real quick here somehow. I've lost my pointer. There we go. Let me mirror my displays and bring up an IDE. Okay. How's that as a font size? It's okay? Okay, I'm going to try this. No, I'll do glasses off. Okay. This is, and how are we doing on time? Oh, we're doing all right. This is just going to be a quick demonstration of what it's like to drive Spore today. Okay, so it's the basic idea is I've got this directory here called history, and it contains snapshots of what a particular source code file, anchor.rs, looked like over several commits in its lifetime. I'm going to start at one of those versions, and we're going to create an anchor for it, and then use Spore to continually update that anchor as I put new versions on top of it. So we're going to simulate a development cycle, several development cycles. So I'm going to copy history 00 anchor to anchor.rs. So I'm going to close this history here. So now we've got anchor rs looks like this. It's a bit of source code, about Rust source code, and we are going to create an anchor on this line here. And we're going to see that that anchor follows that line of code as we make all sorts of changes to what's going on. So if you don't know Rust, they have this packaging system tool thing called cargo that's kind of the entry point to doing everything. So I can tell cargo, please run my program. In this case, that's Spore, and run init. And it runs pretty quickly, and it actually compiled and ran there. And it created this new directory called Spore, .spore. So this is the repository directory. So now if I say cargo run status, right, it's going to tell me, it's going to say nothing. I don't have any anchors to talk to you about, so everything is kind of cool. There's nothing for you to think about. I'm going to now add an anchor. So this is worth breaking down a little bit, I think. I guess that's the hardest part for you guys to see is at the bottom there, isn't it? I apologize for that. So this is the metadata. You echo in some YAML, and you say add to this file. I'm going to anchor.rs, create an anchor pointing to that, at offset 46, and it's going to be 20 characters long, and it's going to have a 10-character before and after context on each side. So if I run that, thank God that worked. Okay, good. I found a bug in things this morning, and so kind of with bated breath up here. This is what it spits out. So we can see, at offset 46, this is the topic here. That's that. Let me make this permanent and open up anchor once more so we can see that. So before vec string, right, so we've anchored this bit here. And we can also see some before and some after. So, okay, that's all pretty straightforward so far. And still, if I ask for the status, it will tell me, yeah, there's nothing to talk about. So just, I guess, to orient you a bit more, this finished and running, that's cargo outputting stuff. That's not Spore outputting stuff. Okay, so let's start doing some development. If I now copy version 01 of anchor rs over the top, you may not, yeah, we've added some includes here, some using statements. So we've bumped our data structure down a little bit. And if I ask for the status, it will tell me, anchor A78 blah, 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 blah is out of date. So it's taken the context in that file, compared it to the source file, and say, I no longer match that source file. It's a simple comparison. I don't match. In fact, I can ask it for the diff. Oh, sorry. Cargo run diff A7. And it will show me the diff. This is not terribly useful, but it was easy to implement, so I added it. What we want to do now is have Spore automatically update our anchor for us. So if we look at, this is the thing that's going to change, right? This is the number that's going to get updated when I run update. So I say cargo run update. Update with no arguments just updates everything that's out of date, and it'll run. And we see it updated that to 194. In fact, if I go to this file and I put my cursor there, we see that this is offset 194. I have it, it's in the bottom toolbar. That's offset 194 into my file. So Spore's done something pretty reasonable there. And this was not the most complicated change. Right? We just added some header files and things got kind of bumped down. That's a pretty easy one. So let's go through a few more iterations until we get to something more significant than that. So if I copy history 02 to anchor, I say cargo run status. Again, it reports that we're out of date. And I'm going to run update one more time. I like watching this file as we do this so we can verify that things are changing. I run it again. It updated to 201. So something moved the anchor once again. come down here, copy version 3 into place, run the update. Oh, it updated once again. It seems like I removed some stuff from the file. So let's look at the status of Anchor RS now. This is still pretty familiar. I'm apparently futzing around with the modules that I'm using and pulling in, and maybe messing around with some of these. I don't even know what those are called in Rust. Decorators, let's call them. We're getting very close to a much more interesting update, I promise. So we'll copy 04 in place, and it looks like we added some stuff down here. And if I run update, it's happy. So we're about to do a pretty substantial change. I'm going to copy version 5 of Anchor into place. We've had some insight into what our data structure should really be shaped like, and now we've made a big change. And I make that edit, and OK, I've changed the shape of this context struct, the thing that we've been pointing to. I've even changed the data types that I'm pointing to, right? So the signature, in a sense, of the struct has changed. If I come here, this is telling me offset 184, and offset 184 is way up in here somewhere, way out here. So we're clearly off. So is Spore up to the challenge? You know the answer, because I wouldn't do this demo if I didn't think it was. But yes, it handles this. To my surprise, it handled it quite well. So I'm going to run update. And indeed, it figures out where the anchor is supposed to be. And in fact, we can see that it's even seeing the new bit of code. So that is a very quick demo. There a question? Yeah.
So the context is really just the post, right? So if you had a longer context, presumably it would have struggled more with that kind of a change.
Yet so the question was, if we had a larger context, say it was 5 lines of code, would it have problems with that? So I think that yes, that would present certain challenges, because lots of little changes could happen inside there. At the same time, you have much more to match on as well, so that might bump the score up in the Smith-Waterman run. The TLDR answer is I'm not entirely sure. There's so many moving things in here that it needs to be explored. I have played with larger things, harder to demo kinds of things, and it seems to do the right things in those cases as well. So I think the algorithm scales well with, scale is the wrong word, but it behaves well with larger inputs, because you just get bigger scores, and you're looking for a maximum score, which is part of why that works. All right, so that's the demo. Let's go back to the slides here. And actually, that's really all I've got. So thank you. I think we have plenty of time if we want to take some questions or anything like that. So thank you. Right.
So have you run it on anything but source code? Does it behave well with more or less structured data?
Have I run it on anything besides source code? I have probably run it just idly on some open, natural language text, but not with any goal, just to kind of see if it worked. And it's never not behaved on things that I put into it, because I don't see how it would be sensitive to the differences between source code and natural text. Although I may be totally off base about that, but certainly I'm mostly just concerned about source code. Yeah?
Would you try to label sort of other, because source code very structured, it's a limited vocabulary in a way, and there's a lot of, at least if you look at the white space, it's sparseness in it. Whereas, so I say natural text is different, there's a lot of data input that would sort of mimic source code more than anything. Presumably it would work well with that, so you could out-of-band annotate even large data sets with interesting metadata, right?
Yeah. So the question/statement was that you could if this worked with other kinds of text, you could in principle use this to annotate more or less anything. And yeah, that's true. You could annotate, I think, books. You could annotate actual data, maybe even if you got CSV files and stuff like that. I don't see why it couldn't work on essentially anything. Yeah.
Did you try to version it?
Say that again.
Did you try to version it? Like you put it into Git or track Git history that way? Is that something you might even do if you would check it into your repository?
Oh, so the anchors. I mean, yes, I envision the anchors being tracked, because if I've associated so yeah, do I want to revision control the anchors? Yes, I think that would be a sort of a normal thing to do, because if developer 1 has created some important anchors about the thing, and developer 2, clones or pulls or something like that, they would want that data as well. But that's an interesting question. Maybe we need some way of having, anchors that follow the code around, and then also private anchors or something like that. That's another open question. I mean, so far the only user of this program has been me. So if it works for me, then I kind of feel, yeah, it serves my purposes. So partly this is a call to, if you're interested in this kind of stuff and you think it's neat and you want to contribute, we're wide open for that kind of stuff. Yeah. Okay. Oh, sorry.
Presumably it's not limited to text. It's any. You use it on binary data, right?
Yeah, so the question was, is this even limited to just text? Could we use it on essentially anything that we could tokenize? And I think that's true. I mean, the core algorithm doesn't care about really the nature of what you're putting into it. It needs a score function, the two things that are being scored, and a gap penalty function. And with that, it can give you a score.
You can make very interesting tokenizers to even sort of shape, compare different things.
Sure. Yeah. So what he said is that you could create interesting tokenizers over other kinds of data that let you, shape or attach data to, or somehow reason about almost the data. I mean, we'd almost certainly run into some complexities with using Spore directly for that, because Spore is, I mean, you can see its data structures are kind of very text file oriented, but maybe that's just something we need to think about, and we need to refactor Spore, because you could totally see this being applied to, I don't know, a database or something like that. If you could somehow, fit the database into a shape that could be streamed into the algorithm to do the matching, then you've got a tool that can help you realign metadata with arbitrary data. And that would be interesting as well. Okay, well, thanks again for your time. I'll be around a little bit today, maybe not tomorrow, but if you have questions or anything, you can email me or tweet, or if you want to work on the project, I'd love to have your help. Thanks again.